Okay, that's good. It should be working now. No, is it? Can you see it, Kevin?
Yeah, I can.
Okay. Okay. So the difference between electromechanical 5S, a 35S, and then the 45S. So with this one, when I was talking about it, this is set up to how we wire for three-phase 3-wire delta. That each one of these would be a connection for the three-phase 3-wire delta. That in a solid-state meter, where you have auto-ranging potential coils, like the 35S that we used when I was in Utah from, that's not the color pen I want a different pen here. When I was in Utah working for Utah Power, we used an ABB meter here that was a 35S. It was a solid-state auto-ranging alpha meter. And the auto-ranging meter, in order to be auto-ranging, all the potential coils in the meter have to be tied to one common point. So when we used the 5S previously had 2 points where each potential coil was separate. And so you had to, if you're on a 3-phase 3-wire delta, you would put a jumper in between these two. And you'd put B phase here, and that would fit with Blondel's because you're measuring current in A phase, measuring current in C phase. B phase is the unmetered leg, but Blondel says in order to meter this correctly, you have to have a tie to the conductor, which is the B phase conductor, with both potential coils, or a common tie to both potential coils. So that meter comes out. We install the 35S into the same socket. When we do that, this jumper is okay to leave in place, because if I leave it in place and make the connection here between the two and still have B phase here, nothing inside the meter is connected to this terminal, and so leaving this jumper in place will not hurt anything. But if you were installing a new one, you'd really only have to put B phase to the right center bottom terminal, because the potential coils in the 35S are tied to that point. And so you wouldn't have to have the jumper, but if you have a jumper and replace the 5S with the 35S, then there's no problem just leaving it wired just exactly like it was. When we get to the 45S, this was a GE meter that was an equivalent of the electromechanical 5S. When you would take the 5S out of a socket and replace it with a 45S, when you would do that, same idea, the jumper was still in place. B phase connected between these 2 points. B phase connected between those 2 points. All the potential coils in my meter, where now I've got 3 potential coils. I have a potential coil connected from the blue terminal, that's the center left on top, down to the common point where all the potential coils in this meter are connected. And so as I look at this one and B phase jumpered across the bottom, there's a potential coil that's connected between these two and the 45S. There's a potential coil that's connected between those two and the 45S, but having this jumper here really nulls that out. That even though there's a potential coil there, both sides of the potential coil have the same voltage on them, and so this has no effect in the metering. And so A to B voltage across one potential coil, same as the 35. C to B across the other potential coil, same as the 35. And so that's how we would replace a 5S with a 45S. And then back to the idea, if I would put a new one of these in, and it was on, all of these are for 3-phase 3-wire delta, and I'll show you a diagram here in a second. All of these are on the same one. This jumper sits in place, and I'm going to install it in a new one. I really only had to put B phase to this terminal because I really don't have to have it here to null this one out. I just have to make sure that B phase is on the opposite side of that potential coil, and on the opposite side of this potential coil. And so, having all that said, I'm going to a diagram for three-phase, three-wire delta. It's one of the things we talked about last week is how the vector diagram would be set up for the meter itself. That this is for what would be seen as ABC phase sequence. That the first potential coil in my meter in all three meters has A to B voltage across it. So in the 5S, A to B voltage across this potential coil. In the 35S, A to B voltage across that potential coil. In the 45S, A to B voltage across that potential coil there. In the other potential coil, C to B voltage would be across in the 5S, C to B here. In the 5S, C to B, 35S, sorry, C to B. And then the 45S, C to B. And so that's how all, well not all, the potential coils in the meter are set up. Again, with the idea that I'm metering the current in the blue phase, which I'm calling A phase. I'm metering or putting a CT in the red phase, or what would be C phase. And this conductor, the current that flows in this conductor goes unmetered. There's not a CT here to measure it. And so Blondel says if I have 3 wires, I need 2 meter elements. Each one of these meters is a 2-element meter. And then for the connection to be correct, the conductor that goes unmetered has to have a tie to both of the potential coils in each one of these 2-element meters. And so that's how that goes together as far as the metering, and how a 5, a 35, or a 45S would see that load. See that load, see whatever load that's connected to it. And so as we see this, again, if I was going to install one new, and I was going to put a 35S into this installation, I really don't need to jumper these two. I would just have to connect to that terminal, and so I would just bring B phase up and connect to there, and that gets B phase to the non-polarity side of this potential coil, and B phase to the non-polarity side of that potential coil. If I was going to install a new 45S in a 3-phase 3-wire delta, again, I don't need to put anything on this one, just need to put it there, because that will get non-polarity on the blue and black coil and non-polarity on the red and black coil. So the 3-phase 3-wire delta is pretty straightforward. Hopefully we don't do a lot of it anymore. It's something that there's lots of it from my past over in Utah. We had lots of it out in the fields where we had pumps and that type of thing. It's not always that it had a CT meter on it. Often it would have a 12S meter on it. Doing it with a 12S, which is the 2-element equivalent of the 2-element meter. That's a solid state meter, where the 5S, 35S, or 45S are the 2-element instrument rated meter.
Question for you: do you still have a lot of your downtown stuff as deltas like we do
In Utah?
in Seattle?
Yeah, there's lots of stuff. Not right in downtown. Right in downtown, not as much of that, but from about where the stadiums are going south from there, lots of delta in that area. Mostly 4-wire delta, not a lot of 3-wire delta in our system, but mostly still lots of delta out there, lots of open delta banks, and then some that are wired with, and most of them are wired with 2 CTs, that type of thing, and that's what the one we're going to talk about next. So
We still have a lot of our stuff downtown. I still run into 3-wire deltas on some of the really old stuff.
do you?
Yeah.
Yeah, in Seattle, like I say, south of downtown, and it would, like I say, start about where the stadiums are and go south from there. There's a large industrial area in there, and lots of that is three-phase, 3 or 4-wire delta with more 4-wire delta, a lot more 4-wire delta than 3-wire delta, but still, there's enough 3-wire delta out there that we still have to take care of. So, any other questions on this? So now we're going to look at 3-phase 4-wire delta with the same meters. 3-phase 4-wire delta, when we do it with a 2-element meter, we're not doing Blondels. With the 3-phase 3-wire delta and a 5S, 35S, or 45S, any one of those are Blondels, but this is not going to be Blondels. It's something that we're tricking Blondels by making the connection we're going to make. And so the same setup, the meters are no different, same exact metering. I've changed all the colors to match the drawing for the 4-wire delta. And so we'll go to the drawing for the 4-wire delta so we can see what is happening in the 4-wire delta with 2 CTs. That, again, this is something that Wally and I would have grown up with as apprentices and did a lot with when we were journeymen in the field. Lots of 4-wire delta. Not always did it have CT metering on it. We had a 15S, but for the largest proportion of our 4-wire delta, we did just like this. 2 CTs. The 8S meter, we didn't use the 8S meter much. It was something that was uncommon to put an 8S meter on 4-wire delta. But as we look at this and see the 4-wire delta, what happens in this one is that we take we have 3 energized phases and then the neutral, which makes up the 4th wire in our system. And so, according to Blondels, if I have 4 wires, like 4-wire delta shows here, I should have 3 meter elements. Again, we're going to trick Blondels, take it clear down to 2 meter elements, save the cost of a CT, save the cost of potential coil, and an element in our meter. And again, this is how we did most of our 4-wire deltas, just like this. So from our 3 energized phases, 2 of the energized phases that come off of this blue phase that goes through one way on our CT, the black phase that goes through the opposite way on our CT. This theory that is sitting right here is the exact same theory that we do with single phase CT metering with a single CT. Exact same theory sits right here that's in the single phase CT metering. The other CT is, by CT size, is half the size ratio-wise. So whatever this ratio is, if this ratio was, in this case, we'll say 400 to 5, this CT, where the high leg is, would be a 200 to 5. And so as we would wire them like this, you'd end up with a 400 and a 200 sitting out there. What would happen with the 400 is we'd see the 400 with 2 turns on it, 1 turn on the blue wire, a 2nd turn on the black wire. So we take our 400 to 5 or 80 to 1 ratio divided by 2, and that would give us a 40 to 1, which is the same ratio as this. And so again, this is the common way we did it, is have one phase going through one direction on the polarity side, the other phase going on the non-polarity side, and this is the only way I can wire it to make it so the current that flows in this CT will add together from these 2 phases. If I try to put them in the same direction, they'll subtract from each other. So this is the way it has to be done in order to get the wiring right. Again, this is the high leg, and it only has single wire going through the CT at half the ratio. And so looking how the vector diagram is here, at the vector diagram for the transformer connection and for a three-phase load that's here, and that's what that says here, that this is the transformer vector diagram that's here, that if you have these drawings that you purchase through the Meterman's Bible, something just to be aware of, that the color code of these inside vectors that make up the delta shape here, that this blue vector that would be here, and the red one and the black one, those are the transformer coils color coded wise. And so as I see blue, that would be this vector, the blue vector would be this coil, the red vector would be this coil, the black vector would be this coil, and then the dots that connect them in the corners here, I'll zoom in a little bit so you can see what I'll just pick these two up like this, that these dots that sit in the corners here are the jumpers that make up the transformer bank. And so where blue and red come together, where blue and red come together, that's this dot right here. Where red and black come together, red and black come together, this jumper that makes up the delta bank is that dot right there. Where black and blue come together, this dot right here, where black and blue, that would be this jumper here. And so if you have these books, that's how the books are set up as far as the vectoring of the transformer coils, and then the vectoring of the transformer coils will relate to what goes on in the meter itself. So I'm going to zoom back out. So in this setup, I've got three currents for my three-phase balance load. That's what it says here. I'll zoom back in here for a second. So it describes it, the secondary vector diagram, ABC phase sequence, balanced three-phase load at unity power factor. At unity power factor, this is where my currents sit. Now, if I was to draw these currents and extend them all the way inside to the delta, I'm going to bring this current down and bring it inside the delta and make a dot right there. So I'm just extending the length of that current. I just want to show you that as I do this, that these currents end up being, let's see if I can get this one up where I want it. Same spot, about, not perfect, I cheated a little bit. And here, that as I look at the three currents that are IA, IB, and IC, and see the phase relationship of those three currents, they sit at 120 degrees out of phase with each other. So from IA to IB, it's a 120 degree phase shift. From B to C is 120 degrees, and then C back to IA is 120 degrees. So those three currents, and in a balanced three-phase circuit, and we can go back over here for a second just to show you what I mean, whether it's three-phase four-wire delta with a balanced three-phase load, or three-phase three-wire delta with a balanced three-phase load. I'm going to do that for here too, as I draw this one back into the, that's not a very good line, but it works for us. Draw it back into the delta, draw it back into the delta with a balanced three-phase load on any, on any one of the three-phase three-wire delta, three-phase four-wire delta, or three-phase four-wire Y, that the balanced three-phase load will create three balanced currents that are going to sit 120 degrees out of phase. So keep that in mind. With a balanced three-phase load, that's what your expectation should be, is 120 degrees between the phases. As we go back to where we were, 120 degrees between the phases. And so as I look at from the transformer vector to what the meter vector looks like, this is what the meter vector looks like for the two elements of my meter. Element number 1 is in this meter. This would be element number 1. That's what we'll talk about now. So this is a 2-element meter, element number 1, and then element number 2 here. I'll put a 1 and a 2. So those are 2 meter elements. So element number 1, as far as how the currents are wired in here, IA current goes through the CT in its H1, so it goes in H1, goes out of H2, and then goes off to the load. As we look at the black current, or the IB current, it goes into this CT backwards. Okay, so as I look at IA in my vector diagram, same direction as what it's in the service, or what's feeding the customer, same direction, same magnitude, and so that one is going through in and through on polarity. The one that goes into non-polarity, again physically, this is, they're put in opposite of each other. The one that goes in non-polarity, that in the system, this is, it's 120 degrees out of phase with the other two. It sits out here, but by me putting in this backwards, it takes this current and sets it up here inside of the what's going to become the what is seen as minus IB, where here it's IB, this is minus IB. So those two currents combine, again, as I see them, the direction and the magnitude will be exactly the same here. Direction and magnitude is the opposite, but the magnitude will be exactly the same. So IB is here, minus IB there. And then these two currents are being added together. This is the addition of them through vector addition. That if I take minus IB and shift it over here, IA, and put it there, I end up with a resultant current inside of that CT. That is the combination of those two that is described, and I'll zoom in on that one so we can see a little better, as IA minus IB current is what that current is, and that's this summation of those two. So at a balanced three-phase load, the magnitude of this current ends up being 86% of what they would be added together directly. We won't worry about that other than it's 86% at 240 volts. Over here, it's a full current value at 208, and so I have 86% of the voltage here and full current. Over here I have 86% of the current and 4 volt full voltage. And so in this 2-element meter with that 3-phase load, I'd get the exact same amount of torque out of this element as I would this one. And so that's something that's pretty cool in this one. And like I said, if we went down and actually got the numbers here, we could prove that if I added IA and minus IB together, I'd get 86% of them here at 240 volts. I would get full current here at 208 volts, which is 86% of that. So I get half of my torque on my meter here, the other half of my torque on my meter here, and so a nice application here. Even though it's not Blondell's, it works out pretty well how it's wired there. Somebody was smarter than me to figure out how to do that. So
those unity power factor in a balanced system, right?
Yeah, that's exactly what the vector diagram is unity power factor and a balanced 3-phase load. So in my first element, as I look at, and I'm going to pick up from here, look at the vector diagram compared to what the metering is seeing, that in the potential coil, in my first element here, on one side, I'm going to put A-phase voltage on my potential coil. On the other side of my potential coil, I'm going to put B-phase. And so across this first potential coil, I get A to B voltage. And that's this voltage right here, which is 240 volts in our system. just so we can see and prove that, from the blue and black conductor, which is the voltage across that potential coil, between blue and black, as I look right there, there's 240 volts between those two. So blue to black really ends up being the voltage across this coil right here. So I look at that, that's the voltage across that coil right there. This is a 122 40 volt secondary coil that's connected in a series connection. So I end up with 240 volts across there. From A to B shows 240 volts here also. So that's what that coil is that vector, and its magnitude is 240 volts, same voltage across this element in my meter. So we'll zoom back. Oh, before we go, I want to show you, not going back and forth will be easier, the voltage across my other potential coil is connected from the high leg voltage to neutral. And so in this system is 208 volts, and that's the vector that would go right up the center of here, from the neutral point to the top of my delta shape from how my transformers are connected together, or from green out to orange. I'd have two coils, this coil and this coil, to get out to there, which going across the blue coil here, we go across this vector here, going across the red coil would be this vector here, and if we were to take those two coils, add them together, the voltages from those two coils is not going to be 120 plus 360 volts. It's going to be 208 volts, because these two are not in phase. If they are in phase, then my red line and my blue line would be going the exact same direction. And so since they're not in phase, it's not direct addition, it's vector addition. And so that's where 208 volts comes from, is from that coil and that coil. Or if I want to get to 208 the other way, I can go across this coil and this coil, across this vector and this vector, to get to the exact same point. So from neutral to this point out here, which is the orange conductor, which could be on either end of that jumper. I could put it on this end of the jumper or this end of the jumper, because those points here and here are the same electrically, and so as that jumper sits in there, I'm able to get that same point on either side of that. So that's what the voltage across my second potential coil, C to neutral, is across there. So that's the two potential coils. And then, as far as the currents that flow in this one, across, or the current that flows in the first element's current coil, again, if you own these books, the reason this is blue and black is because of what this is, that the summation of those two currents becomes a vector that I've drawn in as blue and black. And so if you see blue and black on drawing, that's what I'm trying to show you, that this is the summation current of what's happening between minus IB and IA, creating this current here that sits right in phase with A to B voltage. So the summation of those two currents, two balanced currents, that again you saw where it came from here, being reversed in that CT, puts it here. Summation becomes this magnitude here, which I said is 86%. But this current, I tap the screen with my little plus sign and zoom in. This current in that voltage sitting right in phase is what's happening inside of this meter element. So current through that current coil, the summation current with A to B voltage across that potential coil. In the other element now, we have a second CT that has IC current in it. IC current is the current that's going to flow through this current coil here, with C to neutral voltage across our potential coil. And so again, these two are sitting right in phase, and like I said 10 minutes ago or 8 minutes ago, the magnitude of this current is the same magnitude as these two, but when I add these two vectorially, I only get 86% of what the full current would be. And so 86% of this one, 86% of that one would give me the magnitude here. But I have 240 volts across my potential coil. Sitting right in phase, I'm going to get that torque of 86% of those two added together at this 240 volts. And the other element, I'm going to get C to neutral voltage, IC current. C to neutral voltage is 86% of this voltage. This is 100% of this current, and so I get equal torque from each one of my meter elements. So that's what's happening with the 4-wire delta with the two CTs, one CT with A to B in it, the other CT with a high leg current or IC in it, A to B voltage across this potential coil, C to neutral across this potential coil. And so I'm going to take you back to the, and maybe we can just do it here since, let's do this. I'm going to zoom out just a little bit. Zoom in like this. And look at the 35S now. So for the 5S, my potential coils were separate. Okay, I could put B phase here, I could put neutral here, and these two potential coils would have two separate voltages on it. A up here, B here, C here, and neutral here. So that's how the 5S would sit in this socket. Black here, green here, orange there, blue there, A to B voltage, C to neutral voltage. As I would take this meter out and replace it with a 35S, as I plug the 35S in, as I see the 35S shows the potential coil from where is A phase. Maybe I'll label those real fast. How it was wired for, oh, I need a pen. But this set is A, and this one was B, and this was C. And this is the potentials. The currents don't change from 35, 45, or 5. The currents are all the same. It's the potentials that end up changing. I need a green. So this is how the 5S is wired for a 5S, a 35S, or down here below is a 45S. We'll look at it in a second. Oh, this should be neutral.
I have to say that neutral.
Yeah, that's my first mistake this year. How's that? Maybe just my first mistake today. Maybe it's the first mistake tonight. So that looks like neutral. A lot better than C. Okay, so this is how it's wired. This is the meter sitting in. I'm going to replace it with the 35S. So I pull up the 5S electromechanical. I plug the 35S into this, and the 35S, because it's an auto-ranging meter, the potential coils in the 35S, just like it was with the 3-phase 3-wire delta, are both connected to one point in it. Okay, that instead of coming down and being connected here, in the 35S, there's nothing connected to this terminal in the meter itself. It's connected from here to there for the first potential coil, or this is, maybe I'll draw some rectangles here again. This is a meter element. That includes that right there. And then this would be a meter element that shares that same point. Over here, two separate potential coils. I drew two pretty symmetrical rectangles. Here, this potential coil is connected to neutral. This potential coil is also connected to neutral. And so as you look at this on how it's connected from the socket, as I plug that into the socket, I have A phase here. I have B phase voltage, B phase sitting here. Nothing connected to that in the meter. See here, and neutral here. This is our neutral, that green. I'm just going to set it right above there. And so as I look at the potential coils, when I plug the 35S into that socket, A to neutral is across the first potential coil. C to neutral is across the second potential coil. And so instead of having A to B voltage like we had with the 5S, I have A to neutral voltage.
Which is 120 volts.
Yeah, exactly. And then the other element is exactly right. It's no different than the first element here. C neutral voltage, IC current. But instead of having A to B voltage, I only have A to neutral voltage, which, like Kevin just said, is 120 volts. But in order to do the metering right, I need to have 240 volts. This is how I do the metering right. And so what happened is we had some of these meters come out when we first started buying these ABB meters. They were marked as a 5S. They were marked as a 5S. They were wired just like this. And the meter manufacturer, we started installing them. Wally, I think, was involved with that part of it. That as the process started to come about, there was an identification that that 5S meter wired that really was a 35S. It wasn't this meter. Because it was an auto-ranging meter, the potential coils had to have a common tie for them. So it really was a 5S meter. It was marked as a, it really was a 35S. It was marked as a 5. And so we had these meters installed in the field, marked as a 5, really a 35, and as the meterman would go out and do stopwatch tests as opposed to load tests from their power mate they were using, we found lots of metering errors because this marked 5S meter was not working correctly with that phase to neutral voltage across that potential coil. So ABB went back, I can't remember how long, 2 weeks, and says, okay, we're going to send you a new meter. We're going to label it now as the 35S, which it was all along. But when you put it on 4-wire delta and the second element has 208 volts across it, that this 208 volts, that is the C to neutral voltage. When it has 208 volts across it, the 35S is going to, in its brain, take this 120 volts here, multiply it by 2, so it'll be 120 volts multiplied by 2, so it's just something they do inside the meter itself, multiplied by 2, would give them 240 here, and so now the 240, that was 240 up here, this 240 volts from a phase to neutral voltage of 120 volts is now multiplied by the current in this current coil, and they would have correct metering. All of the 5S meters that were mismarked, we went out and replaced them. It was something that we did those and got them all supposedly out of the field. This happened in probably 1992, I would guess, and I was visiting Cedar City, Utah, and they had changed theirs out supposedly, and we found one in the field that had been in the field since the early 90s with a billing error in the field from the old 5S that they sold us at first, but we got new meters replaced, the 35S for the 5S, and somehow it slid through the cracks, and there was a meter that had been sitting out for multiple years with 120 volts being metered with this current rather than the right meter at 240 volts metering that voltage with this current. And so if the load was really balanced, I'd be off by what would be this voltage of being 120. this voltage being 208, so I get half of the torque of my meter here, and then half of what I should get out of here, instead of getting what I would get if I had the right meter, the 35S, that did this math inside of the meter. So that was the 35S. Like I said, we changed a lot of those meters out. There was just a process that you had the meter, you'd have a list of where the wrong ones were, and you'd go out and get the wrong one out and put the right one in. But there were at least one that I was aware of that slid through the cracks there in Cedar City. So now for the 45S. So as you look at the 45S, I'm going to zoom out for a second so I can get the 45S on our sheet. I didn't mean to zoom out that far, but I think I can do it from here. Okay, here we go again. Oop, didn't mean to do that. Just touching the screen. There we go. Why did I do that? That was the laundry of it. Try this again. Oh, I know what it did. I got to come out again. Let's do 100%. Do from here. Okay, so same vector diagram as we always had. Same vector diagram here. 35S here. Same correct metering because they multiplied this 120 volts to create a voltage that says 240 there. With the 45S, this was the GE replacement for the 5S. When we had the 45S, same vector diagram, like I said. Current inside both CTs exactly the same. Like I said, the current hasn't changed. It's the potentials that are being affected through this process. What I'm going to do here, so I'm just going to pick this one up. If I can, oh, just a minute. Object, unlock, all. Okay, I'll pick this one up here, and we'll take it with us. Shift, Control G, if I can, which I should be able to. Okay. Control C and V. So I brought the vector diagram down to the meter here. So this is the 45S. It's different than the 35S. It's still a 2-element meter. And I'm going to zoom in and we'll look at it first. So the 2-element meter here, as I look at the elements on this one, I'll get my red pen again. The right-hand side element is exactly the same in all 3 meters. The right-hand side element, this element, is exactly the same in all 3 meters. Phase neutral, high leg voltage, and IC current flowing through that element. So this is element number 2. For element number 1 now, again, includes that connection there. Element number 2 has, in this meter, in the 45S, 2 potential coils. The potential coil is connected from, if you remember what our meter was wired, has a phase here. That's how the meter was wired in the socket. I mean, how the socket was wired. I said the meter, how the socket was wired. So, socket was wired A and B, and then C. And I'll get this one right this time, Kevin. Neutral. Okay. Neutral here. So that's how the socket's wired. And so I pull the 5S out and plug this meter into it. And what I end up with now, like I say, the same current flows in this current coil in the meter that has in all 3 elements. That hasn't changed. Same current flows in this current coil as all 3 elements. Same potential that was across the 5S had C to neutral across it. The 35S had C to neutral across it. The 45S has C to neutral across it. So this element in all 3 meters is wired exactly the same, and so it's not the effect here that we're worried about. It's with the 35S, they doubled the voltage across this potential coil. In this one, as I plug this one in, B phase voltage has a place in this one. And so we're not going to multiply anything in this one. We're going to measure A to neutral voltage across my first potential coil. Again, solid state meters that have auto-ranging coils in them have to have a tie with all the potential coils to one point. So A to neutral across one. We'll do C to neutral next. And then B phase in our socket has been here all along. With the 35S, it just ignored this one. With the 45S, they actually use it. And so across this potential coil now, B phase is sitting here, neutral is sitting there, and so this one has B to neutral voltage across it, A to neutral voltage across it. So in the 45S, they take these two voltages and they add them together to where A to neutral plus B to neutral is going to create voltage A, B. And so A to neutral and B to neutral is going to give us AB voltage, which 120 plus 120 gives us the 240 that we're looking for. And so over to our vector diagram now. Our vector diagrams, I got to push me out a little bit here. Our vector diagram is looking for 240 volts across this potential coil with this current being the exact same current that's been flowing in that element all along, whether it's the 5S, the 35S, or now the 45S. This combination current of these two, this current here, is the current flowing in that current coil. The voltage across these two potential coils is the voltage AB, and so voltage AB with that current is going to give me correct metering. C to neutral voltage with IC current, C to neutral voltage with IC current is going to be correct metering here, and so that's how GE did their equivalent of what would be the 5S. Now, if I find this one in the field, I'm going to replace it with this 45S. I really don't have to rewire anything. I can pull out the 5S on the 4-wire delta, plug in this 45S, and these are the marked voltages. Let's zoom out a little bit and see if we can pick up the marked voltages from our socket. A phase, so A phase voltage there, A phase voltage here, B phase and B phase, so that's the same, C phase voltage and neutral, and so same thing here, A to neutral and C to neutral. Again, if this sees 208 across this potential coil, it multiplies this voltage by 2. Now, when this meter is in 3-phase 3-wire delta, the voltage across this potential coil in 3-phase 3-wire delta, because this is B phase, and it would be C to B voltage, it would be 240. So with 240 there, we'll go back over to that drawing. Just 1 second here. That is, I'll zoom in here a little bit. That is, we look at the voltage across this potential coil, again over on when I'm using it on 4-wire delta, it would have 208 across it. I'd multiply this voltage by 2 when it's on 4-wire delta. On 3-phase 3-wire delta, this would have 240 volts, and so it doesn't multiply this voltage then. So when it has 240 volts across it, it doesn't multiply that voltage. But if it has 208 across it, like on 4-wire delta, it's going to multiply that one. So in this one, as we look at the vector diagram for this one, zoom out just a little bit, maybe to 200, the voltage across A to B voltage is 240 volts, C to B voltage is 240 volts, A to B across there, C to B across there, and so that's how the 35S fits with the 3-wire delta as opposed to the 35S on the 4-wire delta. Does that make sense? Any questions?
Hello, Brad.
Hi.
Wally.
Hi, Wally. Your microphone's working.
I just dialed in. So, this is a really good memory of what I used to do. Don't do this much anymore, but really good.
That's good.
Your apprentices should really take you up and watch and go through these with you.
Yeah, this is something that we learned from Alan Besant. Not the 35 or 45, but the 5S. Wally and I were apprentices together, so yeah, we have a little bit of history. Wally started like 3 days before me at Utah Power over in Salt Lake back in 1975. So
Coming up on 40 years real fast.
that's a pretty neat number, Wally. That's cool. That's awesome. It's fun that you came in tonight. You were involved with this, weren't you? With when the 5S's, seems like I remember that.
Yeah, right at the end of it. Yeah.
They sent
we had to change out a bunch of these.
Yeah, they sent.
And we had when they started doing these, and we had the Fisher Pierce.
Yeah.
Analyzers, trying to get those to match up with the analyzer. It wasn't so good either.
Yeah, that's right. I remember that too. Good for you. That's a little more history that's there. Yeah, it seems like they sent us something that says if we were to use the VTs with it, then we wouldn't have to worry about it. Is that right? Do you remember that part?
Yeah, I mean, you're really taxing my memory here.
Yeah, I think the VTs, if you put VTs on something like this, you would have on the secondary side of the VTs, you'd have a common conductor, and so that common conductor could go to that neutral point, and it would end up being right. But that's something I remember them saying now that we've been talking here. So
yeah, we had to turn the clip upside down to get it to work. You had your A and then the B and C, and you had to turn it upside down.
Yeah, that's pretty fun to have some of that other stuff coming back. So yeah, that was a fix. So that's good. I'm glad you're here, Wally. Congratulations on your new job. That's pretty cool for you.
I don't know, but appreciated you doing this. It was good to sit in on it.
Yeah, we try to do it every Monday night. We won't do it next Monday night because it's a holiday, but the following one will start with the 6 and 36S, how they differ, and then from there I'm going to take and show you what happens if you have a 6S that is connected into a 9S meter socket, what the error becomes. And so I'll do that one after we talk about, similar to this drawing that we're looking at on the screen here, where I go through and talk about how the 6S will be different than the 36S. It's a lot simpler discussion because there's only 2 meters, but from there I'm going to talk about having a 9S socket, and a 9S socket where the common was common to 2 points on the right hand side, and so you end up with a metering error that we can talk about after we talk about the difference between the 6 and 36S. So that's in, not, like I say, not next Monday, but the next Monday. So anybody that's interested in seeing that one, make sure you come back. And then from there, next thing I have on tap is to talk about this stuff, talking about open-circuited CTs. So we'll talk about open-circuited CTs and what the electrical part of it is. There's some very sensible pieces that goes into what causes high voltage with an open circuit CT. That, just to kick this off so you have an idea where I'm going to go, with our power transformers, distribution transformers, that type of thing, they're a constant voltage device and a variable current. The current is determined by what the customer has on, but the voltage doesn't change because the customer turns on a light bulb. The voltage stays very stable. So that's what our power transformers or distribution transformers would be. But with a current transformer, it's a constant current device and a variable voltage device. So it's different. So we'll talk about that. And like I said, this will probably be in 3 weeks before we get to this one. But so if you're interested in that, come back in 3 weeks. So, but you're always welcome. All of you are always welcome every night when we do this. It's fun to have some new names all the time. That's really cool. So it looks like it's just about 6 o'clock. Like I say, nothing next week because it's President's Day, and I was president of my Metergod group in high school, so I get to celebrate President Day. So I get to be one of the presidents. So if you're a president,
It's a better thing.
So
well, you're president of the class, so we'll celebrate your birthday again next week.
Yeah, that's it. So
We just had a CT open circuit inside itself and kind of eats itself up.
oh, that'd be interesting to hear about. So if you get a chance, come back and tell us about it, Wally.
We're, it only loses a third, right?
When the CT
Was
disappears.
it Y? Was it
Yeah, that's what
or Y or Y with one CT that open circuited for about 30 months? So not too good.
Wow, yeah, that's pretty intense. That's pretty intense. So, okay.
I got a story too. I'll tell you about that Mike Shaw did to me one day when we were at Goshen on a 400 MVA transformer. He opened one up.
Oh, was it blue flame?
It was really different, Brad. It started shooting molten copper at me. You know how you are in the back of those cabinets doing your wiring. Well, he opened that up, and next thing I know, he's shooting molten copper at me, and so I had to call Portland and tell him to dump the transformer now.
Wow, that's kind of spooky.
And then he got to go meet with the vice president.
That's not good. Okay.
Before you run away, I've got another one for you that I ran into this week.
Okay.
We have a 1S meter that is 480 volts.
Yeah.
And all of your electronic meters, they don't make them in Rexes, which is your standard one. So we had to order a special, basically like an Itron Sentinel, in order to get it to do it. But they're going to have to wire it so that it will do a 1S function.
Do you have any 2S's that are 40 volts?
No, not that I know of, but this is a really strange one. They use it for straight lighting for the state, and it's a 480 volt phase to neutral transformer.
Yeah.
So, interesting.
Yeah, if you look in your Meterman's handbook, Kevin, there are some places where they take a 2-wire circuit and meter it with a 3-wire meter. So if you come up with a 480 volt 2S, you might be able to do it that way rather than have to get something outside of the, outside of your system.
Well, they're gonna make one for us, but it was interesting, when you're put your voltmeter on it and you go phase to ground, 40 volts, it really wakes you up.
Yeah, I bet.
Anyway, I'll let you go.
Okay, well, good night to
the
the
class.
rest.
It was very interesting.
Yeah, make sure you come back again.
I will. I'll be back for the 36 and the open CTs because I've had a few of those.
That'd be great. Okay.
Thanks, Brad.
You bet.